For this problem, we are given f of v is equal to e to the negative absolute value of v, and we are asked if you substitute tau, does it work or represent an autocorrelation, or if you substitute omega, then does it represent a power spectral density. So autocorrelation, the criteria would be that it's even and that the Fourier transform is non-negative. So if you substitute tau into this and you do the transform, so e to the negative absolute value of tau, you do that, it's 2 over 1 plus omega squared. From that you can tell that it is non-negative. So that's criteria 1. And you also see that e to the negative tau is an even function, so it can represent an autocorrelation. So the condition for the power spectral density function is that it's greater or equal to 0, so it's non-negative. And you can see that if you plug in omega for v, that will always be greater than 0, so it can represent power spectrum. So for b, we're given this function, f of v is equal to sine squared of v over v squared. So we do the same thing, we plug in tau. You see that this is an even function off the bat. And if you do the Fourier transform of this, you see this function, which shows that it's positive, so it can represent an autocorrelation. So this is not necessarily, this is not non-negative because sine will be negative sometimes. So it cannot represent a power spectral density function. For c, we're given this function, so f of v is equal to 1 if the absolute value of v is less than or equal to alpha, or 0 if the absolute value of v is greater than alpha. So we sketch it out here. So you see it varies from t minus alpha and t plus alpha. We see that it's an even function. So if you do the Fourier transfer of this, you get 2 of sine of alpha w over omega, which again could not be non-negative, so it cannot be autocorrelation, cannot represent autocorrelation. So if we replace it with omega, we see that it is always greater than or equal to 0, so it can represent a power spectral density.